Alright, so if you haven't seen my last video, I made a game using the EV engine, the game engine that I'm developing, and I showed off how sucky it was. And that's because the engine kind of sucks too, but it's a work in progress. I'll link that video at the top if you want to go and check that out. But I have been working away at improving the way that the game engine handles assets, and that's what I'm going to be explaining today, so that you can tell me whether you think it sucks, or if it's rubbish, or if you like it, or whatever, or how I can improve it, and then we can go from there. I think we should kind of draw this together, and I'll explain what it did before and what I'm doing now, and then we can look at the code a little bit and show you some examples of what it did and why I chose to design it the way I have. Let's go. All right, let's have a quick crash course on what there was before. So we've got Dan the game, right? And inside Dan the game, we've got a bunch of ECS systems. And these ECS systems all do their own stuff. Now let's just quickly write this out. Don't worry, I'll make it bigger. We'll zoom in on this. And then we've got the physics system. I can spell. We've got the render system, the projectile system. We've got the Dan system, and we've got the follow system. Now, all of these, well, not all of these, but some of these systems need to render things. So the projectile and the Dan system. So let's just take a quick look at those. So if we look at the Dan system, it needs to render entities, and those entities are Dan. And when those Dan get created, those entities, a mesh component entity gets added. So if we let's just copy this. And then let's say we've got like a function called create Dan. Every time create Dan gets called, it needs a shader program. And a texture. Well, a 2D texture, because at the moment we're just using cubes. Shader program. So the way that current Dan system works is on initialization, it creates this texture 2D and shader program, and then these get copied into the entities every single time. So this is loaded from a file, and then the shader program is loaded from two files. The vertex shader and the fragment shader. Now, this is okay. This is okay. Texture.jpg, vert.vs, vertex shader, and frag.fs for fragment shader. Now, this is okay. Like, if you were just using these one things, like, yeah, okay, it can load it. Maybe the system shouldn't be loading it. Also, there are probably issues with kind of different operating systems and hard coding paths. Yes, that's a problem that is fixed in the new thing, and I'll show you that afterwards. But the problem here is that the projectile system also uses this same files. So the projectile system at the moment is effectively this. If we just copy this, and we can just rename this. And this isn't great because now we've got these files being loaded, and shader programs being compiled and linked, like additional resource when they don't need to be because they're just using the same thing. And then we've also got texture 2Ds effectively also being loaded and being used twice, and that's not necessary. So what have I done to improve this? Let's take a look. So what did we do now? After. So now, this is Dan the game. Dan the game. And we've still got a bunch of these systems. Let's just copy them. Save some time. And this was here before, but I didn't draw it before. But this is the like EV application that you inherit from to get access to the engine's kind of capabilities, and that the application exposes interfaces for you to do. And I've added a new one called the asset manager, like asset manager. And this asset manager allows you to now access 2D textures, shader programs, and models. So let's take a quicker look at the asset manager itself and its implementation. So the asset manager at the moment exposes 3 functions. Get model, get texture 2D, and get shader program. Now this is just, the shader program one is just temporary until I fix the rendering, which is after this. So we've got these 3 functions, and the systems now can grab a handle to the asset manager interface, call these functions with an argument of the name of the asset that they want, and the asset manager will give them back an asset handle. Now the way that I'm doing asset handles is through an asset proxy. And this asset proxy, it doesn't need to be that big. We can go smaller. Asset proxy is templated on asset type. So a system will say call get model, for example, or the application. The application will then, the asset manager will look for that, return back either a good or bad result. And then if it's good, inside that good result, we'll have an asset proxy of your specific type. So model, texture 2D, or shader program at the moment. Now this asset proxy is a way for me to handle kind of resources. No system owns the assets or resources. Only the asset manager owns the assets and resources. And this is so that I can handle in the future kind of lazy loading, parallel like asset loading, like parallelizing it in another thread so that your kind of system can do what it needs to do. It can stream assets, for example. It can also destroy and deallocate assets if there's nobody using it anymore, which is great. Or for example, like we could almost like LRU cache assets, or like if something hasn't been accessed recently, then yeah. And we can do all of that by the asset proxy. As long as we keep the asset proxy interface with the user the same, the actual implementation underneath doesn't matter because we've abstracted all of that away. Now, the thing that I like about the asset proxy is we can use move semantics to create effectively our own shared pointer here. So, and I'll show you the code later. So you can copy the asset proxy as much as you want, and it's very cheap to copy. You don't own the data. You're not copying the data around. The asset proxy just has a handle to the data, the underlying data that the asset manager owns. You can move the asset proxy, for example, through move semantics, which will effectively kill this one and then make this one valid. The way that the asset proxies are working is reference counting. And I could have used a shared pointer here, but I don't necessarily like shared pointers for this type of design because I don't want shared pointers effectively own, all shared pointers own access and ownership of that resource. But I don't want that in this scenario. I only want the asset manager to own the resource so that it can handle what it does. But I want the asset proxies to inform the asset manager or be the way that the asset manager can understand what is existing out there. So every time an asset proxy is constructed, it increases the reference count of that specific resource. Every time an asset proxy is copied, it increases the reference count. Every time an asset proxy is moved, it does nothing because now the previous asset proxy is dead. It doesn't reference anything. It's an invalid asset proxy. every time an asset proxy is destructed, it decreases the reference count, or if an asset proxy is manually destroyed, it decreases the reference count. And this way, it means the asset manager can own all of its data. It can also handle how many people are currently referencing this particular asset to know whether to destroy that asset or not. It's meant now that if we go back to this system here, if we just copy these, for example, this can be replaced. Let's just delete this. Delete. Oh no. Delete. So here we can have like texture 2D, and that this is the texture 2D of dandan.jpg, for example. We can very cheaply copy that. Sorry, I've lost complete control of my mouse and brain. So we can copy that asset proxy here. So now both systems can have an asset proxy, but they don't and haven't loaded the assets themselves. They also don't own the asset, which is great. They just own a handle and a reference. Now there are two reference counts of this proxy. Similarly, we can do the same with the shader program now. Wow, I really can't use my computer. So we can shader program, and then let's call it like it was called shader. So now both of these have access to a shader program and an asset proxy that can be copied to the component. Much quicker to copy. You're not copying like a bunch of data. You're just copying like an asset proxy, which is at the moment just like a pointer and some metadata about the asset that you're actually referencing. And yeah, you've gone from having to load the same textures and the same shaders to compile a link to now only having to load it once, and then you can just pass these proxies around without being worried that, for example, it's going to get cleaned up or it's inefficient. So there we go. Let me know if you've got any questions about that in the comments. I quite like the design, but they might have some flaws that I'm unaware of. And yeah, let's take a look at the code now, I think. All right, here we go. So I know it's boring, but let's just start with the unit tests because it's a good demonstration of the API, and also like I can show you a bit more about how it works. So here we create a mock asset manager, and the main thing here we're doing is I'm not testing the asset manager itself. There's very little kind of going on there. It would be better to test it, but I haven't. The main thing I'm testing here is the asset proxy because I really want to make sure that I'm increasing the references and decreasing the references like when appropriate. So this current mock asset manager returns asset proxies, and you can see here you can get texture 2D, which returns a result, and you can check if the result's good. If it's good, then you can access it, and you can see, is the asset proxy valid? Make sure that the asset proxy doesn't have a null pointer in it. So get returns the actual asset pointer, and then the texture reference count is effectively just making sure that everything's doing right. So copy assignment, copy constructor, make sure the reference count goes down when the destructor happens, move assignment, move constructor, and then also copying into a vector and checking reference counts there, and then also overriding asset proxies in vectors and stuff like that. There were just edge cases that I wanted to handle. So maybe we could take a look at gets the actual asset proxy itself. So I've got a bunch of these aliases, texture 2D asset and a shader program asset. They're just templated asset proxy types. And then if we look at the asset proxy, it provides access to assets loaded via an asset manager. The intention behind this class is to allow multiple non-owning references to an asset. The asset proxy will be returned by an asset manager to a loaded asset. There's a bit more about the design decision, but we've kind of discussed all that already. So we have a default constructor. We have a copy constructor, which, like I said earlier, you increase the reference because we now have 2 references to a asset proxy. We have a move assignment, which does nothing because it makes the new asset proxy the valid one and the old one have nothing in it. So we effectively null pointer the asset that this proxy is looking at. We also don't touch the metadata because the asset proxy is invalid. We make it false. The copy assignment effectively checks if it's valid. If the metadata doesn't equal the other one's same metadata, then we decrease a reference. If it does equal the same, then we just do nothing because we're just copying the same asset effectively. Yet we actually do the copying here, and then we increase the reference count of the asset manager. Move constructor, same. Destructor, this is where we decrease the reference count. Is valid is where we check whether the asset proxy is valid. There's an also overrided operator to check if the asset proxy is valid. There's both const and non-const gets. And then there's also a manual destroy. And then there's a private destructor because I don't really want anybody creating asset proxies unless they are default constructed here. And those default constructed are by default invalid asset proxies. So only the asset manager should be able to create valid asset proxies, or you get moved or copied asset proxies from other asset proxies. That's a lot of asset proxy talk, but yeah, you get the case. So the design decision for weak pointer, for example, this is because the asset proxy needs to have a handle to the asset manager. What happens here is the application, where is it? Here does a make shared, and in the asset manager, I inherit from enable shared from this. And what this does is it allows for me to give out a shared pointer of the asset manager to the asset proxies. But instantly inside the asset proxy, I convert that into a weak pointer. And this allows me to first, it's like a control plane. So you can check that the shared pointer, the underlying pointer to the weak pointer, so the asset manager here, is valid before you access it. And also it's another way to kind of avoid that ownership thing. So I don't want the asset proxy to own the asset manager handle, whereas I could have just passed shared pointers around inside the asset proxy, but when you destroy the asset manager, it wouldn't be destroyed because there are still references to it in the asset proxy. But really what I want is the asset manager to be able to be destroyed whenever, and then the asset proxies go, is this still a valid shared pointer? If so, then lock it and let's increase or decrease the reference. Now, it may turn out that this isn't very performant in situations where asset proxies are being created or copied quite rapidly. And if that's the case, then we can probably remove this and then just make sure that we are strict in not having any asset handles. Like making sure that asset proxies are only handled in the ECS in your kind of components, and therefore everything gets cleaned up nicely because the engine handles that rather than you having asset proxies being kind of thrown around after the engine has destructed. Now, let's go to the Dandan system. So here, now what do we do? Asset manager get texture 2D, text. If the result is good and the texture is valid, then great. Same shader program. If the result is good, as in it could find a shader and a dandan2.jpg and compile the shader, then perfect. If the shader program is valid, then yeah, again, we're good to go. So then if we check what we do with these actual things, now when we create our mesh component, we just copy that asset proxy into the mesh component. You can see here, texture 2D asset. And yeah, good to go. We now don't have, this is, I've just realized that this is fixed in another branch, but if we look at the actual text, the texture being copied, this is a texture 2D, so this is an actual asset proxy. So we just copy the asset proxy around. And then what's quite nice is that if we read the logs, creating texture asset from here, from this path, creating shader asset from this path, and then here we can say shader program shader already exists, reusing, shader program shader exists, reusing. And this is when it just hands out another asset proxy with a handle to that resource. All the other assets here though are like unique, so they're not being reused. However, I also hope that you can see the speed up in load time in comparison to when I did it last. And yeah, it's a pretty significant speed up. Now, I did cheat slightly by reducing the texture size because the textures were silly big and they really didn't need to be. But this has helped a lot in regards to not recompiling and linking shaders every time. So yeah, I'm really happy with the way this has worked out. It's much quicker to load. I now know what all the assets are doing, and the engine has control over those. The user doesn't have to worry about kind of lifetime necessarily, as long as they've got a handle to the asset. The reference counting seems to be good. The unit tests are backing up any bugs there, or catching, or allowing me to add more if I do catch bugs. It works really well with my ECS system, like straight out of the box. I didn't need to do anything, just perfect. It also, if you see here, I had this comment from 2 months ago, how do we handle cleaning up these resources? This is great. Now I can do some fancy const extra stuff in the component array. Yeah, here. So when I remove a component, if it gets to the point where that component needs to be destroyed, well, generally it always needs to be destroyed, I have a compile time if const expra, and if that mesh component inside the ECS as a destroy function, then call destroy. And that means that now I can clean up my assets, I can clean up my components perfectly, and I don't have to worry about it, because previously I was doing everything through RA. I wasn't doing everything through RAII. If we look at vertex buffer, for example, we have initialize and destroy, and it's like, well, how do we clean this stuff up? But now we can just add the destroy and we're good. Okay, so slightly longer video, but hopefully informative. A few things that I didn't go over in regards to the asset manager design is that everything now is loaded from relative to the executable and where it lives and is being launched from. It will look at an asset directory relative to that binary, and then look in models for models, textures for textures, and shaders for shaders. And so it's very, very simple. Hence why when you saw the API and it was kind of get texture 2D dan.jpg, it will go to that asset directory, look in the texture directory, and if that file exists, it will load it. And if it doesn't, it will return a bad result. So it's very good for checking for errors, also like super user friendly and much more efficient now. And you can see that in the way that it loads. So super happy. Let me know what you think. In the next video, we're probably going to do rendering, simple rendering, just so that we can remove all of the gunk that Dan has to do itself, and also means that we can move towards adding kind of lighting and things like that, because we'll have to make that acceptable. And also, again, abstracting away all of that stuff from the user and making it much easier to kind of add models or draw models wherever they want, which again means the renderer can be really dumb and stupid at the start, but because we've abstracted it away, we can then start to become more efficient. Yeah, thanks very much for watching. Let me know what you think. Again, subscribe, like, whatever you want to do. Really appreciate you watching, and cheers.